Let's wrap up chapter 3.1. I have just a quick notation thing. I think I've seen students make mistakes with this where they're given a function, they take the derivative, and then they say equals 0, and then solve for x, which is pretty much the right thing to do. But then somehow they start thinking that f prime is always 0, regardless of the x value. So I would avoid writing this. Just take the derivative, say here's the derivative, and then ask a question. Where is this equal to 0? And then solve for x. I have a puzzle for you. If we find a spot where the derivative is 0, is that a guaranteed local min or local max? We saw before where we saw a derivative was 0, it wasn't a guaranteed global min or global max, but is it a guaranteed local min or local max? See if you can think of a counterexample. Pause the video. All right, welcome back. So a big counterexample is x cubed. X cubed looks like this, right? Right there, so this is x cubed. F prime is always 3x squared, and here's 0. F prime at 0 is what? Just 3 times 0 or 0. Is that a local min or local max? Well, is it larger than all the points nearby? Well, it's larger than all the points to the left, but smaller than all the points to the right. Is it, so that's why it's not a local min or a local max. So we can say it's a spot where the derivative of 0 is not guaranteed to be a local min or a local max. We can say this is a saddle point, that's the name of it. They're more interesting in higher dimensions. If you think of an actual saddle on a horse, it goes from the left, the point in the center of the saddle. If you go left and right, it's at the largest point as you go from left to right or right to left. But if you go from front to back, the saddle is curved up and down, and so it's a local maximum left to right and a local minimum front to back. Saddle points are important in machine learning, deep learning stuff. Because in high dimensional spaces you can kind of get trapped there because the derivative is kind of 0 there. I mean, it is 0, but you can still do better by going a different way. So it's something to watch out for. Except it's hard to watch out for it in high dimensions. In 2 or more dimensions. And it happens in machine learning, etc. Computer optimization. Okay, so then a third big thing to wrap up. We were doing our optimization on a closed interval where we had a definite start point and a definite stop point to the interval. So if you're optimizing on not a closed interval, like maybe you're optimizing on that range, what could happen? You could, so we'd have like an open dot here, and it might do something like that, and then an open dot here. Does this have a maximum in that interval? Well, you can get larger and larger values as you go here, and you never quite hit one value that's the last value. You can always get closer to that last endpoint. Or another option would be something like, does e to the x on, let's say, 0, infinity, that's not a closed interval. Here, let's divide this. It just keeps rising. Does that have a maximum on the interval? Well, no matter what you think might be a maximum, you can always go 1 unit farther and get an even higher value. When we're saying, so that's one example. You could also say something like this. If that keeps rising forever, you have a local max, but there is no global max. So those are the things you have to watch out for. If you just take the critical points, it would be those three, and if you just take the highest of them, you could say, if you were careful about it with this x cubed thing, if you weren't sure it wasn't a saddle point, you could say that's a local max, but you can't say it's the global max even though it's the highest of all the things you tried, because you didn't try all these points out to infinity because they aren't critical values. All right, that wraps up chapter 3.1.